Sometimes I get a bit grumpy when I read about chemistry and it's expressed in the sense that some matter is like that, something has this behaviour because of some theory or because of some model. No. Every model, every theory is derived from observations of the nature of the stuff or what it does. It's the experimental evidence that comes first, and the rest of these things that we call theories or models are our attempts, chemists' attempts, to explain at a deep molecular level, often, why the behaviour of the nature is like it is. And I'm going to talk about a nice example of that today, and one which has always left my mind just boggling, and it still does. And it concerns the notion of quantization of energy. So where do we start? Back in about the 1900s, 110 years or so ago, people were looking at the light that was emitted by hydrogen when it's energized to such an extent by heating or by an applied electrical voltage that it existed as hydrogen atoms. And the light, the radiations that came out were analysed in the same way that we might white light coming from the sun. We put it through a prism and we can see that every possible wavelength or energy of the colours of the rainbow are present. Or if we like, every wavelength possible is present. Or every quanta of energy, of every possible energy are present, at least as far as we can see in the visible region. There's also other stuff in the higher energy ultraviolet region and the lower energy infrared region. But every possible energy is being emitted from the sun in varying intensities of some wavelengths. When scientists studied the light, the radiation that was emitted by these excited forms of hydrogen atoms, energized hydrogen atoms, and analysed the wavelengths that constituted that light, they've just found something very puzzling. And here's, up on our screen here, the emission spectrum, the wavelengths that are emitted by hydrogen atoms when they're in this energized condition. There it is there.
Sitting one above the other here are four different spectra obtained when radiation from different sources are passed through a prism or, more likely, a diffraction grating. And on the top is the result of that dispersion of light from white light. And every single wavelength, every single frequency or photon energy is in that range of wavelength that's dispersed. The next three, with all the lines on them, are those of sodium, hydrogen, and calcium in their atomic states as vapors. Just focus on the hydrogen one in the middle. There are many, many wavelengths or photon energies which are not emitted from that source. So when the incoming radiation is passed through the dispersing diffraction grating, there are many energies that are simply not there. And there are very, very specific energies, photon energies, or wavelengths or frequencies that are emitted only at those very specific narrow frequencies. Isn't that remarkable?
So essentially, the emission spectrum of hydrogen consists of lines. And what does this mean? It means that there is no light emitted at this wavelength or this wavelength or this wavelength or this wavelength, and that very sharp wavelength, there is emission, there is light emitted. None at this wavelength, none at this, none at this, none at this, none at this, but there is at that. None at this, none at this, none. There is at that, and there is at that. So only certain frequencies or wavelengths or energies of waves or quanta are thrown out. Why would hydrogen atoms, when they're energized and sending out light, radiation, only emit light of that wavelength or energy, that wavelength, that one, and none of these in between? This is an enormous puzzle for scientists back then, and caused quite a lot of controversy. And probably a major step was made by a scientist called Niels Bohr. And he suggested that the only explanation for that is that hydrogen atoms have only one electron, and that this electron in each of the many, many hydrogen atoms that are in this energized condition can only have, the electrons can only have that much energy, or that much energy, or that much energy, and actually he could make a pattern of these getting closer and closer in such a way that we have a correspondence there, a powerful argument. So what he said was the electron can only have particular energies. This is called quantization. In other words, this electron cannot have that much energy, that much energy, that much, that much, that much, that much, that much. It can only have this or this or this, according to his idea. Now, just imagine, you're on your bike. If you were quantized like the electron of hydrogen atoms, you might be able to ride at 2 kilometers per hour, and you want to go faster. You can't go to 2.1 or 2.6 or 2.8. You can only go to 3.3. And then if you want to go faster again, you can't go to 3.4, 3.4, you can only go at 4.8. That's the next level of speed. Nothing in between those things. Right? Imagine being able to walk at this pace, and I want to walk a bit faster. I can only then walk at this pace, but nothing in between. I want to walk faster, this pace, nothing in between. Quantization, just astonishing. And this idea created lots of controversy back in early 1900s. In fact, it was only 1897 that a guy that we now know as J.J. Thomson had provided evidence that electrons existed. It's only 120 and a bit years ago. Before that, no one even knew the existence of electrons. And now here's this other Charlie saying, not only we acknowledge the existence of electrons, but it can only have certain energy levels. How does this explain that? Well, let's suppose that this is the first energy level, the second one, the third one, and the fourth one. In the condition where you have these hydrogen atoms, either very high temperatures or the electrode potential across them, the electron has energy in some of these higher energies, levels. And what it does is it always wants to come back to the lowest, like water rolling down, ball rolling down a hill, water flowing down a hill. And so if it's in this level, if it's been energized up to there, it can go back to here. Right? Now remember, this plot is energy, not distance. Energy. How much energy does the electron have? It can emit that much light. It cannot emit, let me do it in different colour, it cannot emit that much light or that much light or that much light, because it would take it to a state that can't exist, not allowed, we say. Alternatively, we can have a change, a decrease of energy from, if it was existing there, from the third level to the second level, or the third level right down to the first level, or from any one of these to each other down to there. Now, it just happens that he could make the correspondence between this difference of energy of the quantum is the energy of that wave that's emitted. The energy of that wave corresponds to the energy that's emitted when the energy of the electron goes from there to there. If you let out some water from a vessel and you take it from 10 litres down to 3 litres, 7 litres has gone out. This goes from this energy to this energy, this much energy is emitted, and there it is. And this one corresponds to, say, this one. And so on. Now remember, I'm only talking conceptually. I'm being a bit loose, and things are more complex than this, especially when we come to things which are not hydrogen with just one electron. But the idea of quantization and spectra that can be accounted for by the differences between the allowed energy levels of electrons, and furthermore, these differences happen to be in the region of the radiation spectrum which is in the ultraviolet or the visible regions. Right? So many of the solutions that we see of all sorts of things are coloured, and that's because not they're emitting, but because they're absorbing, going up to higher wavelengths as light passes through them and we see what comes through. So this is only because these differences are in the visible and the ultraviolet region. Just happens to be that way. Now let's go beyond atoms. The same principles apply to molecules, but things get more complicated for molecules, and we finish up not with lines, but some bands later. Now, molecules have other ways of possessing energy, not just the energy of the electrons, but they can have energy of vibrations. So, for example, think of a water molecule. It can be one of them amongst the many, many, many. It can be vibrating in many, what we call modes. It can have, I'm a water molecule, oxygen, 2 hydrogens. It can have stretching vibrations. And not only that, these stretching vibrations, this one is faster than this one, and yes, you've guessed it, the vibrations can only have allowed levels. Quantization of the vibrational energy levels. Now, as well as the stretching, that's one form of stretching. That's called symmetrical. Here's another form of stretching, asymmetrical. And here's another form of stretching, bending. And each of those 3 modes can have different energies, but only of allowed levels. So if we have, let me now jump from this being an atom to a molecule, and that's gross. I'm talking conceptually. If you have a molecule in which the electron is in the ground state of energy, electron energy, it can have for any one of those 3 forms of vibrational energy different quantized levels. And now change up or down from one energy level to the other gives a delta E, which corresponds with a line in the spectrum, either of absorption or emission. And it just turns out that these differences in energy levels are smaller than those, smaller energy levels. So the light corresponding to delta E that's either emitted or absorbed is a lower energy, longer wavelength. And these ones commonly correspond with the infrared, these ones commonly correspond with the infrared region of the spectrum. A bit longer, less energy than these jumps. And chemists can do an awful lot of analysis of structural characteristics by looking at the infrared spectrum. What is absorbed by different substances? All right. So again, I'm flashing up here now is the infrared spectrum of several substances.
Firstly, here's the infrared spectrum of water. When radiation of all wavelengths is passed through water, in the vapor phase usually, some in the infrared region, some absorption happens. You probably won't be able to tell from the label on the horizontal axis at the bottom that this is that these frequencies are in the infrared region. They are, and the label, the vertical axis is of amount of radiation transmitted. So there are three regions where the amount transmitted is very low, and that's because in those regions the radiations are absorbed. And those absorbed radiations are particular to transitions, absorptions between levels of vibrational mode, quantized allowed levels. And here is the infrared spectrum of carbon dioxide, in this case with labels telling us specifically which vibrational modes are contributing to the absorptions. So take the middle one, symmetric stretch. The absorption that's happening there corresponds with the energy of photons that are those that are absorbed to take any vibrational mode from one energy level allowed to other allowed energy levels of vibration. And the difference between those corresponds with photon energies in the infrared region.
We'll certainly be looking at the infrared spectrum of carbon dioxide in respect of global warming, because that is the key element to this phenomenon of global warming, all due to changing of its energies of vibration. Now, I suppose that would be the only form of energy other than electrons having more energy and vibrations? No. Molecules can have another form of energy, and that's what we call rotation, actually tumbling over themselves, either in the liquid state or the gaseous state. And it can tumble slow or it can tumble fast. But the energy of tumbling is quantized. And now, actually, for each one of these vibrational modes, we could have very much finer, much closer together quantized levels of rotation. So the switch, the excitation or de-excitation between energy levels of tumbling, of rotation, are much smaller, much longer wavelengths, and these spectra can be detected in the microwave region, right in the long, much, much longer than the infrared region. And that to me, just the very phenomenon of quantization. And I can't give you a reason for that. It's in quantum theoretical postulates, which you may or may not learn about, except for now that this explanation satisfies these sorts of ideas incredibly. And it's the evidence that came it's the evidence that came before the model. Mm-hmm.